Perfect. So let me close this thing. Perfect. So hello everyone again. After 1 week, I was on vacation actually. So now I'm back, and we want to talk today. I think both this morning and this afternoon and today, and then I'll go so you will be free. Talking about NLP. So in the past 2 weeks, you have seen some stuff that's already covers the background that we need to do today. Even with just the stuff that you have learned, you can already do some NLP tasks. But here we will go in depth over some advancement of NLP research and new stuff there over the past, specifically over the past 5 years or 6 years, because this has been a very hot topic. We will touch on very recent issues that people are dealing with right now and what is left in the research for NLP and this kind of things. But before that, we would build the blocks. I hope this would be interesting for you. Actually, I was also inspired from several courses that have been recently developed for teaching NLP, such as CS552 here, which is a very interesting course. Like if you want to do I think it's offered in the master's and PhD program here. I don't know about bachelor, but I think it's offered in the master's program. If you are a master's in computer science here, you should take this course because it's too exciting. So yeah, let's jump in and have a brief overall review of anything that's on discussed today. So this is too boring for you. We have all these deep neural networks that you are all expert with. And remember, we could play with the architecture a lot. So we had several takes on the architecture. We had the CNNs, and also we had the time series stuff that needed recurrent neural networks. If you remember, time series was any data that is measured at regular intervals, step by step, that has an order. And if we did a permutation in the data, the semantics of the data changed. So this was the topic behind time series. We said that we could use time, we can build models to classify a time series or also to forecast. We also use these two exactly in our lecture today because text is also a time series, if you remember. So if we simulate a text using time series, the first time step, second, and so on. And as a result, we can use text-based models to do both classification and forecasting. An example of classification is, imagine you are given a text and you will find if, for example, this sentence is happy or sad, or an email is a spam or not, or any kind of this classification tasks on text. So as you can see, we can just do a classification. And forecasting is also easy. It's also common. In text, you can also predict the next word that comes. This helps in building chatbots. When you ask a chatbot a question, it should provide 1 word, 2 words, and like complete a text for you. And that's a specific example of the forecasting task. So both tasks can be used for NLP. I think the stuff is easy, so I'm just reviewing them. And as we saw, recurrent neural networks were good for time series, and that can also be good for NLP, any kind of text data. You remember everything, right? So this was the cell that had hidden states at each step, and it was passed to the next state over time. So the model updated its hidden state over time from the sequential input, and then we used, for example, the last layer or something like that for the prediction, and we can have a small feed-forward network or anything on top of that to do our classification or anything else, for example. Then we saw LSTMs. That's a solution to mitigate the vanishing gradient problem for long sequences. Specifically, long sequences are very important in text because our texts are not usually short. So in a time series, we can have a window of 4 or 5, but in text, it's usually window of 4 or 5 is nothing. If you ask ChatGPT a question, it's usually multiple words. And now people are building text models that work with 1 million tokens, 2 million tokens, such as Google Gemini, I think. So as you can see, this problem is very important in the domain of text, that you need long sequences. And thus people first started using LSTMs to also help in the task of classifying text time series. So we remember all of that. The thing that we want to mostly discuss from that lecture today is the sequence-to-sequence models. I hope you remember it. If not, everyone remembers sequence-to-sequence, right? Yeah. So you remember it, perfect. There was an input, a set of encoders, and a set of decoders. So this is the general construction. And a lot of tasks can be represented like this. We even we're talking about some NLP tasks that can be represented like this, such as machine translation. This could be a set of words in English, and those could be a set of words in French. It could do the translation. And we can train this model in any task that we want. Remember also the attention mechanism that we added up in RNNs or LCMs or like other recurrent models that that each cell also got input weighted average, or I mean a linear transformation of the states of the RNN cells of the encoder. And we also saw the transformer architecture, which removed the recurrence at all and just relied on the attention mechanism. So yeah, in this architecture, if you remember, we had encoder blocks and decoder blocks again. So the transformer can be used as sequence-to-sequence models. The input can be text, image, or anything else. I think you have seen vision transformers previously, we can assume. But here we would focus on text transformers on two specific architectures mainly about text that I hope would be useful. So this was a transformer in one view, right? So we had the input. We had positional encoding because transformer, due to the non-recurrent architecture, did not take into account the order of the words, or like which words come before which words and so on. So we needed to add a positional encoding that added a certain position information to each word in the sequence so that the model knows which word comes before which word. Then the encoder block consisted of attention over all the input and a feed-forward network, and we also had the layer normalization layers here. So we had n of these input blocks, for example, 6 in the original transformer paper. And also for the decoder, we had two attentions. One among the decoded stuff until now. So this is why it is masked. We don't attend to the tokens that would come in the future, of course. And then another attention on the encoder, on the values from encoder. So by the two attention blocks and also the layer normalization and the feed-forward network at the end, the decoder block is also able to basically decode the whole response that we want for. Then usually there's a linear layer at the end and also a softmax. If you remember, softmax was a function to convert a set of scores into probabilities. So when you want to do classification, for example, classify if a sentence is, if a person that's writing a sentence is happy, sad, or angry, we can have 3 scores for these classes by the softmax function, which is which you basically put all of the scores into exponential function and then take the proportion. In the softmax function, we can find the probabilities. For example, we can confidently say with 80% probability, this sentence is a sad sentence. With 20%, it's a happy sentence. And we can find the probability using the softmax function. So this was the whole transformer. Any question until now from the basically a review of what we saw and things like this? All right. So let's go forward. Let's explore natural language processing as a specific deep learning task. So NLP is not a deep learning task inherently. People have been doing NLP way before deep learning stuff. And we're doing it with a lot of ways. So very, very early systems. I mean, yeah, regular expression, which you may already know, is a certain kind of natural language processing in a sense, you may say. Because in when you write specific rules to find patterns in the data, it's somehow you are taking a text and converting to a format that the computer could understand. So this was very early NLP systems. And you may know, but even with those simple rules, people have built chatbots and intelligent systems. I mean, intelligent at their time. It's not nothing compared to ChatGPT, but at that time they were considered intelligent. So it's not that NLP can only be solved by deep learning, but deep learning has helped a lot. And the system that we have now, ChatGPT, and also a lot of classifiers and things like this, all the large language models are all, of course, without the deep learning revolution, they couldn't happen. Specifically, I talked about regular expression, but one other thing was before deep learning that people use for NLP was simple statistical models. So in machine learning, you can also use very simple statistical models, such as simple regression models, or you may have heard naive-bayes models, to do predictions using a model which is not a neural network, but it still does predictions. And it's called a kind of machine learning. So people usually use that for the domain of NLP, but there were two downsides. the traditional models, of course, they were not too strong compared to neural networks. And the second is that the way to convert words to a representation for the computer was usually done randomly. We will talk about this in a bit, but deep learning also provided some solutions for us later on to find the best way to convert words to certain vectors that computers could understand. So with all of that, let's jump in. As we talked 100 times until now, NLP is any task that works with textual data. By NLP here, we mean any task that works with textual data. Either outputs text or gets input text. So for example, imagine a model classifier saying that if a certain sentence is happy or sad. In such a model, we have three main components. First, there is a sentence that we get input to the model, right? For example, I say, I enjoyed the summer bootcamp. So this is a happy sentence, and the model should say it's classified as happy. So we need some way to represent the word in a computer understandable way. We usually call the equivalent of the word embeddings, and we'll talk about how we can find such embeddings. So this is one challenge. The second is that we need to have a model that gets these vectors that are equivalent of the words as input. And then we need to find a mapping between the outputs of that model and the predictions that we want to give to the user. So you already know steps 2 and 3. For 2, we can use a lot of models that we have until now. Previously, people used RNNs, LSTMs. No, we can use transformer-based models, but we would cover some architectures, specifically that are commonly now used in the NLP world. For 3 is maybe the easiest one. For classification, you can just use a softmax. You can put a model on top of it, or a small model on top of it, or things like this. So you have the model, and you can just easily map them to the predictions. These two are usually simpler, but for 2, we cover architectures. But first, let's talk about 1, which is more specific to NLP. We need to find ways that we can represent words in a way that computers could understand. It may seem simple, but there are some new things that people have done that have helped this process. So we can go forward. Any question about this until now? Is everything clear? Slower, faster? Perfect. Okay. So first of all, before finding any way to convert words to values, we need to convert a sentence to its words, right? So an easy thing can be that, we can just consider each word separately, right? We call the process usually tokenization. So we have a sentence that contains several words, and the computer can't understand the sentence all at once because it doesn't make sense. There are a ton of sentences in the word, maybe the countless amount of possible sentences that you can make from words, and it doesn't make sense if each sentence maps to just one vector. We usually want to have different values for different words, because 2 sentences that have 10 words in common but 1 word different should not be like two very different vectors. We want vectors to build on words, because words are the units that convey meaning, right? So we want to separate the sentence to the word such that we can input the words to the computer. This is usually called tokenization. And because each sentence or each text, not only sentence, I usually call sentence here, but it can be document, contains several words, we need to convert them into units called tokens. So each token is a meaningful unit of characters that has some meaning, and we can use it to train our models, right? This is the whole meaning of token. We somehow are making our sentences discrete into discrete set of tokens. So the whole task of NLP compared to maybe some other real value tasks are usually we work with discrete data, because words can't be continuous. Like we have either this word or that word. We don't have real value data such as different time series. So tokenization also helps us with the process of discretization. So we make discrete values afterwards. Consider the sentence, I'm attending the summer bootcamp. One way to tokenize this, the very simple way, is that we say I is the first token, am is the second token, attending the third token, and so on. And also maybe we want to extract the exclamation mark as another token. So this is very simple, right? This tokenization, you only need to write a split by a space. It's a 1-line Python code, and maybe you can just consider the punctuation differently. I separated the punctuation because, punctuation can also have a meaning on its own. Like the exclamation mark is not a part of the word bootcamp. So ideally it should be separate. But Is this the only way to tokenize the sentence above? Okay, of course the solution is not, because otherwise I wouldn't have written it here. But what do you think is a downside of tokenizing like this? Anyone has an idea?
I think could be anything after attend their attendance and so many prefixes and stuff.
Exactly. So that's the thing. The meaning of attending is not the word attending, but actually the root attend, as an example. So attend is the meaning of the word attending. Because if we do it like this, and then we have another sentence in the document saying, have you attended the summer boot camp? Imagine we have another sentence like this after this, like it's a dialogue, chatbot. Have you attended the summer boot camp? And then I answer, yes, I am attending the summer boot camp. If we token out like this, the word attending and the word attended have two different tokens or two different tokens and would be two different vectors. We usually don't want this to be the case because they are the same. They're just a grammatical difference, right? So it's just a grammatical difference, and we don't want them to be two different tokens. We want them to be the same tokens, but still have the differences because the model needs to usually be grammatically correct. So we want to also teach them the grammar. The way that we do this is usually we separate attend and the ing in many tokenization methods. So we separate the suffixes, prefixes, the grammatical structures of English language and also many other languages into different sets of tokens. This way, also a model can learn that in all present sentences, it should, for example, say the word with the suffix ing, as an example. Like, you are somehow also indirectly teaching the model about grammar, which has been shown that it's more helpful. So here, the one thing that we can do is, yeah, we can separate attend and ing. This way, the model knows that this sentence is talking about the task of attendance because it has the token attend in it. If we don't do this, the model should learn that attending, attended are all the same. It's not obvious for the model to learn this, and that is more difficult. So this is one thing that early people did. Okay, this was the sub, and also there are other problems with considering one word at a time. For example, the word check-in or 6 years old if you put dashes. If you just separate by spaces, it doesn't make a lot of sense because if you consider 6 years old as one word, then 7 years old is totally another word. 8 years old is totally another word, and this doesn't make a lot of sense. We want this to be 6 token years token old, such that the model somehow learns this is talking about their age, right? Or also words such as isn't. This should be also separated into two tokens because isn't is the same meaning as is not, and is not another word, right? So when we separate is not into two tokens, it doesn't make a lot of sense if we keep isn't as one token. And also, as you said about the attending, attend and attending are totally different tokens if we don't do this separation. Why not? Because also the number of words increases a lot for each variation if we don't do the new version of tokening, and this leads into more computation. If we don't separate attend and ing, imagine for every verb, every word in the world, we have a ton of different variations with different suffixes and prefixes. And the size of our vocabulary gets very huge. And like training them would be way more costly, a lot more time. But this way we can keep the size of our vocabulary short. For example, consider a dictionary. It has like many, almost all words in English, but if you wanted to write all words in English, it would be size of 10 dictionaries because the dictionaries usually don't put all the suffixes as different entries, right? If you open an Oxford dictionary, for example, attend and attending are not two separate entities, usually, I think. Otherwise, the size would be exploding. So also with this, we can keep the size of the vocabulary. Vocabulary is a set of all words. We usually call it vocabulary. We want to keep the size of the vocabulary small enough so that our models don't turn out to be very big and untrainable, and yeah, like that. Also, space is not generalizable, tokenizing by space to other languages. Some languages maybe do not use the space as English does. For example, I think Korean, Chinese, and some other languages are different in the way that they separate words, and we usually don't want to build a certain tokenization approach that only works for English because there are a lot of text in other languages. But also consider that even after these changes, we do not usually use the exact same tokenization approach for any language. So the tokenization approaches could be different for different languages or can have different variations, just to have in mind. So this is an alternative that we talked about. I am attend, ing, there somewhere, and also bootcamp maybe could be two words. I mean, this is just an example. I don't know if you put it on a real tokenizer that is used now, what it would separate it or not, but just as an example. So maybe different tokenizers also have different behaviors. If the tokenizer has the word bootcamp in its vocabulary, it would not separate. But if it doesn't have it have this word in the dictionary or its vocabulary, it would separate into the two units of meaning. So this is how the tokenizer works. This is the first step. We take a sentence or a document or anything, and we split it into tokens. Now we have a set of tokens, and the possible set of tokens is also limited. So before that, the possible sets of documents or sentences is unlimited. But if we separate into tokens, each of them is from a set of, imagine 1 billion words. Like English has a set of words, right? Imagine we have a certain set of words, and each word is from that set. However, one challenge here is that maybe people write some words that are not in the vocabulary. Maybe they have typos, or they invent some word, or they just push characters in the keyboard with no meaning. So we usually should have some fallback procedure in tokenizers. There are usually some tokens such as unknown that many tokenizers put them. If there is any word that can't be linked to any word in the vocabulary, we put it unknown. What do we mean by can't be picked? For example, attending is not in the vocabulary, but attend and ing are in the vocabulary. So we can separate it into attend plus ing. But imagine it was a totally random word, such as something like I put like keys randomly in the keyboard. I type keys randomly, and there's a new invented word, and it's not in the vocabulary and can't be split. And we can't also correct it by seeing the closest word from the vocabulary. In that case, we can just replace with an unknown token. Sometimes it usually happens in tokenizing. So yeah, this is about tokenizing, converting a document or sentence into a set of words. Any questions? All right. Perfect. So we talked about vocabulary, which is a set of all possible tokens that can appear in a document. Any token that is not in the vocabulary or can't be mapped, I mean, can't be separated or mapped or can't be linked in any sense to the vocabulary is an unknown token. An unknown is also a token in the vocabulary. So in our set V, that we usually call the set V, I shouldn't put this because this is a sign of the set, but anyways. So yeah, any token in this, not in this set, is an unknown. And we should represent each word of this set as a vector because our deep learning models work with vectors. They don't work with Unicode words. They work with vectors or numbers. I mean, vectors are generalizable or numbers. So we should somehow represent each word in the vocabulary by vector. And then the task are solved, right? Because if all words of a document is mapped into our vocabulary and we have an equivalent vector for each word in the vocabulary, then our task is solved. One early solution can be one-hot vectors. We call it usually one-hot vectors. What does it mean? One-hot vector, if you know, is a vector that one entry is 1 and the rest are 0. Something like this. So we have a vector of the size of the whole vocabulary, and each word, we map it to a certain position of 1 and the rest should be 0. For example, here, we somehow define it that the first position, if the first position is 1 and the rest of 0, it means the word I. If the second position is 1 and the rest of 0, it means the word am, and so on. So this is called one-hot encoding. We usually call it one-hot. This is a very early solution that is very simple. I mean, it's super simple because if you have the vocabulary list, you can just use the index of each word in the vocabulary to define this. For example, if word attend is the 522nd word in the vocabulary, you can have a vector that in the position 522nd, it's 1 and the rest are 0. So this is how usually this is how you can ideally convert words to vectors. And this works, right? This can work because if we have equivalent of each word as a vector, we can put them into our deep learning models as imagining we had a vector, we can just put them into our deep learning models and expect the model to train from it and learn. So this can be a good solution. And I think also some systems in the early days worked with this. So it's not something not totally working, but there is a very big downside as well with this. Anyone thinks of any downsides with the one hot approach? Yeah. Exactly. So that's one thing. I mean, that's actually a good thing, but it's still, after we also solve it, it's still in our current system, the number goes very high. So we still have this problem. People have not yet solved the problem, but because I mean, you're right, but the systems that are capable now, like the size of vocabulary, is almost usually nothing compared to the number of parameters these models usually have, I think. So now the bottleneck, I don't think, is the size of vocabulary in today's NLP systems, such as large language models or so. Now it's not the bottleneck, but yeah, that's the correct thing in general.
Structure to the different terms. I don't know, but I know you're coming to embeddings later, so I'm not sure whether this is the point.
Yeah, exactly. So yeah, you're correct in sense. So here, maybe let's just go to the next slide. Oh, we had the downside here. So yeah, we'll just cover embeddings. You were right.
Objective of it already exists to have
Exactly. Have some meanings for this. So the semantic meanings. That's it. So we want the word vector, these one hot vectors, to contain some semantic information. Here they don't contain any information. It's just a very I lost all of it. Sorry. Here is just a very simple mapping and does not have any semantic information. For example, could you find these two and say, is there any meaning here? Nothing. You should just know the mapping. There is no semantic information. For example, imagine this is a system. This is the vector like for like. This is the vector love, and this is the vector for the word parameter, right? So these are three words from the English language, and these are the three vectors. One has the one in this position, one has in this position, and the other at that position. How can we find the similarity between these vectors? We ideally want the words like and love to have some similarity. For example, be close in the vector distance, maybe, or some similarity. Like here, there are these three. We can like here when we look at these three, you can group two of them together and the odd one out. But in the vectors, you can't do this. So we lose something when we are going to words to vectors. We are losing semantic information. The differences between these two vectors are actually not so different that these two vectors. Actually, parameter is closer to like, I think, than love is closer to like. I mean, this is a toy example, but yeah. But here, of course, anyone who any maybe two-year kid, if you show them like keep the odd one out, like love parameter, they would say, oh, like live, I like them, but what the hell is parameter? So yeah, they would just cross this one. But in the vectors, we can't do this. However, normal time series has semantic information. The numbers that we had in time series task could be huge, small, or have certain patterns. Like imagine you have this sinusoidal pattern that we had covered. So in the normal time series, we had this semantic information because our data was numbers. And numbers, okay, because they were just captured numbers, they had semantic information. Imagine weather temperatures. It had semantic information because anyone can understand that, yeah, 40 degrees means something different than 20 degrees. And the exact numbers that are input to the model are also 40 and 20, right? So normal time series had this information. But when we are going to NLP, with that approach, this characteristic of time series is lost. We lose the semantic information if we do one hot vectors. So we want also in the NLP time series task to also have meanings for word vectors. And that's why people have explored the domain of embeddings. Here we want to find vectors that are, for example, imagine if we have the vector for like, love, and parameter, we want the similarity and the closeness, the distance of the vectors between like and love to be more than the distance between like and, to be, for example, less than the distance between like and parameter. Because like and parameter are two different words, but like and love are similar, right? So we want our embeddings to be, we want our mapping of the words to vectors to also have some semantic meaning, also have some patterns. So this is the whole idea. Any question? All right. Oh yeah. So for that, of course, we should use vectors with real numbers because as we saw with just 0, 1 integers, it didn't work. But how to find them? One idea is that we can have a model to learn them. One possible solution is that we can add feed-forward networks, a very simple feed-forward network, converting these one-hot vectors to real valued vectors. But usually isn't enough. Why? Yeah, I jumped too fast. What do I mean? Imagine you have a task. You have a data set. We usually work with data sets in NLP, of course. Like we have a data set, for example, 5,000 sentences labeled as happy or sad, and we want to classify them. Imagine this is the data set that we have. We usually don't have very big data sets in NLP. Like, I mean, 5,000 is not very big, so we have millions and also billions, but it's not like that. Yeah, the whole Wikipedia text, we can't usually do it as data set because we don't have labels. So for data sets, we need also to have labels, right? If we want to classify between happy and sad sentences, one human should sit and label everything. Oh, this is a happy sentence, this is a sad sentence, and they usually you should pay a lot, and it's usually not worth it to collect very, very big data sets. Like some companies such as OpenAI are like making very big data sets, but in normal NLP research, like in our research, we usually the thing that we struggle with the most is usually finding a good data set. So yeah, we can just in the same approach, we can maybe you can say, oh, okay, we would have the one hot vectors, we would just add a feed-forward network to convert them to real valued vectors in the transformer. Like before putting them into the transformer, we can just put a feed-forward network. This is not usually enough because the amount of text in our data sets are usually not enough for the model to learn good embeddings, to learn good vectors, to find good vectors of the mappings. For example, imagine the same example of love and sorry, the same example of like and love and parameter. Imagine you want to classify, you have 5,000 sentences of happy and sad. How the model should somehow learn that like and love are similar, but parameter is far. Like this is not an easy task. If you imagine you are a kid, you never read any text in your life, and you just see 5,000 sentences, and then you should learn all the words in the. I mean, this is not feasible, right? The computer can't also do this, so it's not very easy to just see 5,000 sentences or a small amount and learn very good vectors for each word. This is not very good and doesn't work well. So why? Because labeled data is usually rare. I mean, rare is not, maybe you consider rare as just 5 or 6, but no, I'm even saying 5,000 or a million could be rare. Because if you want to find patterns in text, there are a lot of words in English. If you want to find very good vectors for each of them, you need to see a lot of text. And we don't usually have them. We don't usually have a lot of labeled text that some human has sat and labeled all of them. And thus, it's not enough to capture enough dependencies between words by just saying, for example, 5,000 sentences. This was a big challenge. So the idea is that, sorry, the text is a lot. We use the vast amounts of unlabeled data. For example, go to the internet and download all Wikipedia articles, or go to some book website and download all books or things like this. You have a lot of unlabeled data, unlabeled, and then somehow use them to find the embeddings. So use a data without labels. Why we do this? The idea is that the amount of unlabeled data is a lot. Just Wikipedia is like maybe several gigabytes, terabytes, I don't know. Like I assume there are a lot of text there, or the internet or websites, encyclopedias. We have a lot of text that is unlabeled. It's not labeled with happy or sad, but it's a good quality text. It may even have been, for example, Wikipedia, there are some people who review and like who correct. So it's also almost high quality text. We want to use them somehow to find the embeddings, to find good mappings of words to vectors. Then we use them, we just get them from them. Then we throw the Wikipedia or any data set out. And now we use those mappings in our smaller model that only trains on those 5,000 texts. So what do I mean? Imagine we want to do a classification of sad and happy on 5,000 text with labels that we have. Instead of just training our data, first, we train a model on the whole Wikipedia. Somehow, I will tell how, to find mappings between words and targets. It just does this. It doesn't classify happy or sad because we don't have any label data in Wikipedia for happy or sad. We just have a model that converts words to good vectors. We freeze that model, we keep it. And then when we want to classify the 5,000 sentences, we want to train that model, we first convert all words in those 5,000 sentences to vectors using the model that we trained on Wikipedia. So using that model, we convert words to vectors, to very good vectors, ideally. And then we just put them into a transformer, those new vectors, and train our task. And this has been shown to be working very well compared to just using one-hot vectors. So yeah, we use the whole Wikipedia that has billions of words to find embeddings, to find very good mappings of words to vectors. Then we use them to train a smaller model on just our 1,000 or 5,000 sentences to classify happy and sad. So any questions? I mean, this is somehow maybe you should say similar to transfer learning. I mean, transfer learning was a bit different because I think you have seen it in the vision lectures. It's changing the model. Here we are not picking a part of the model. It's before that. Like it's in the just part that you want to compare words to vectors that we input to the model. Refresh that part. So any question? Yeah.
Will you explain how derive a good embedding? How you even
How do
say embedding is good?
I see? Yeah. So
Maybe that's maybe.
so I mean the best way I'll show it. I mean we also have a small code that will train some embeddings from a data set. Yeah, we will certainly show that. About how the embedding is good, it's actually a good question. Okay, one thing, so there are some metrics. There are some metrics that you can run on the embeddings. I'm actually, to be honest, not an expert on those, but there are some metrics. And I mean, one thing also is that if it works well in the final model, then it's usually a good embedding. So this is also something that in practice is also very important to us because usually just converting words to vectors is not the task that we want to do. We finally want to have our final model. And if an embedding just changing, you can have the same model, just change the embedding, and maybe will be a better model. Then it means that the embedding is better. I mean, this is something that in practice we use. But I think there are also some metrics that you can find the embeddings. Another thing is that you can do things such as what we did here, not here, in the love and sad. Well, sorry, here. Here we can find the vectors for each word and then compare the similarities. In a good embedding, the similarity between love and like should be more than like and parameter, for example.
But then you need labels.
No, we are not doing labels here. This is before the task of classification.
Yeah,
Yeah, how we're gonna compare it.
exactly. How,
Oh, the two vectors. I mean, the vectors should be closer in the space.
how, but that's a label.
No. I mean, the vectors are a set of values, right? Is a in a multiple dimension, and then you can find the Euclidean distance, for example, or cosine distance.
Maybe that okay, you computed it then to see like if this computation makes sense or not.
But
Oh,
but
okay.
then that's a label saying those two are close and like and height.
Oh, you mean either they're close or not? Yeah, that's the thing.
Yeah.
I mean, yeah. So I think there are some metrics that compare it based on some corpora that have this kind of similarity information. I'm honestly not an expert in those, to be honest, but I can check it. But yeah, the way that we in practice do it is usually put it into a model, and then the model, the final classifier should work better, ideally. And now we have almost very good embedding. So I don't think if there are a lot of new research on this area, but now we have a lot of good embeddings that already work with like GP. Like you can also access one of the leading embeddings. OpenAI API also provides their embedding that they train GPT with. And I think there's an API call that you can just send a string to them and they would return you the vector, which is, yeah. I'll also say how it is useful for and things like that. Yeah, but I will cover it. That's a good question, actually. So, okay. So we are here. And sorry. Well, okay. So we learned about this. But how do we train this model? So we want to train a model that gives us embeddings, right? On unlabeled data. So until now, I think all of the examples that we have seen, I don't know if in the vision you have seen also self-supervised methods. But at least in the weekend over here, all the examples that we saw were supervised. So there were labels, there were things like this. We didn't have a lot of unlabeled data that we wanted to find something from it. But here we want to do this. Imagine we have the whole Wikipedia text and we want to learn something from that data where we don't have labels. We usually call this self-supervised, which means that this is not supervised, but it's supervised from its own. We usually call it self-supervised. In here, we want to find patterns by looking at large bodies of text and, importantly, words that come next to each other or close to each other. So this is the whole idea behind most of the embedding methods. We look at a lot of text and find co-occurring words that co-occur with each other. For example, imagine a model looking at the whole internet. It should learn that Bern, Lausanne, Zurich are usually come in the articles that have the Switzerland in them, so there should be Swiss cities. And thus, the vectors of Lausanne and Zurich and Bern should be close to the vector of the word Switzerland, for example, or things like this. I mean, this is just an example, but in practice, it's also somehow like this. So yeah, ideally, we want our models to learn these kind of patterns from data. Or another pattern was that love and like can co-occur more than love and parameter, right? So the model somehow learns this stuff. And actually, this may seem a bit weird, but it works well. So we now want to cover specifically one approach in the pre-transformers era. We will also talk about the transformers era approach. This was for, I mean, mostly for LSTMs and like pre-transformers methods called continuous backup words, or CBOW. This, what's this? So we just, in this approach, the idea was that we trained a model to predict one word from the surroundings. So in each time we get, for example, get a Wikipedia article or a sentence from Reddit or a Stack Overflow or any kind of text that is available in the world, in a book or anything. We take one word, replace it with blank, and then train a model to predict this word from the surroundings. This is the task of the model. So you can imagine that we can create lots of training examples just from doing this. Imagine a Wikipedia article. You can each time remove one word, and then there's a new entry. So you have a ton of entries without any human labeling. This is self-supervised, right? And then they train this model, they trained this model, and they had also feed-forward networks on front of one hot vectors. Then they use the output of those feed-forward networks to find the embeddings for each word. So in this way, they find the embeddings that this model discovered. And then they can use this for their own specific task. So that's the whole idea. Any question? Yeah. Yeah, this is the model is trained to do this. Get these 5 words and predict the missing words. This is the task of the model. And you can see, you can make a lot of examples like this. No human needed, just the human just only needs to write the code, and yeah, the code can gather information from Wikipedia, replace words, and yeah, predict. So this was the all that. And for this, we are not limited to only 5,000 entries. Maybe we have millions of billions of entries. The more data you can get into the model, I mean, the only limitation is usually the memory and GPU and this kind of thing. Like the code can do a lot. For example, here the model can predict one of the words attending and enjoying. And yeah, so this is the task of the model. So they call it continuous backup words. We have a certain window size in this model. For example, 5 words in the surroundings. We can configure it in the code. So the more words, okay, it has more semantic information, but also takes more time to train. So it's usually a trade-off. We have a certain window size around the word that we want to predict. And then when training the model to predict the missing word, the model automatically infers the embeds in the process by the backpropagation. So this is the whole process. And we can do it on a big corpus. On a corpus is usually a lot of data set. It's a big data set. For example, the thing that we are doing now, which is not a big corpus in today's standards, but we can run it on our laptop, is it's usually used for instructional purposes. Corpus Brown. It's a collection of 1 million words collected from the internet. Okay, 1 million is nothing compared to what GPT and big models are trained on. But if you want to try it on your computer, it's usually easy, and I think It's not very big. So we covered this, but why we don't directly train on the targeted data, on the labeled data? The answer is it's not enough. So usually for something like this to work and give us good embeddings, we need to have a lot of words, at least maybe 1 million. Like 1 million is almost nothing in today's standards, but we need a lot of words. If we have only 5,000 sentences and each of them have 10 words, it's like maybe 50,000, and it's still 20 times less than 1 million, which is not very good. We need at least multiple 100 times more. So yeah, we can see in the code. Let's see together. A very simple code snippet. It's very simple. You can try it yourself.
Must have like no million words.
What do you mean?
I'm just thinking
Oh no, this is not 1 million unique words. This is a corpus containing a lot of sentences, and collectively they have 1 million words. They can be multiple. For example, there are a lot of I, you know, yeah. They're not 1 million unique.
thinking like how many words do we know?
That's a good question. But I mean, also, if you're considering embeddings, it's also other languages. So if you see a model has a vocabulary of 2 billion words, I don't know, but it's usually because it has a lot of like Middle Eastern, Chinese, Korean, all of these they have a different set of words. And if you ask GPT in any language, it will answer you. So the vocabulary obviously also contains vocabulary from other languages. But yeah. So we have also code that's inferred from this website. I will put it in the GitHub. So let's go over here. Okay. So we want to here train a very simple word-to-vec. It's not a very technical thing, just as a toy to show you. We usually, for this kind of early NLP task, NLP before Transformers era, NLTK is a very good library. You can easily install it with PIP. NLTK is a library that we use, also Genesim. So here, NLTK also has a corpus thing that has some corpus that you can easily access without you needing to go to the website and download it. So it has some corpora built in, which is very good for playing with NLP models. So you just import it from nltk.corpus, import Brown. Brown is the name of the corpus that you want to use. The first time you need to download it. This is very nice because it automatically downloads this to a folder that all of your Python code can access. And only I think runs it once. So if you do it a second time, I don't think you download it again, unless you remove the cache. So nltk.download, you put the name of the corpus, and then you can get the sentences. It's very easy, right? You can see there are a lot of helper functions in NLTK that help you play with the corpus without the need to separate everything or tokenize everything and things like this. It takes care of all of them. So NLTK is a good library for this. We won't go deep into NLTK but yeah, you can see something here. So I run this code because training the model takes a long time. So I run this at home just yesterday. So yeah, then you just it's very simple to define a word-to-vec model. Model equal word-to-vec. Word-to-vec is the name that the authors of the paper, I think, wrote for this model that converts the words to vectors. But specifically, word-to-vec is about the approach that we are using. It's not any embedding, right? So the new embedding methods that we would see are not word-to-vec. Word-to-vec is this specific approach. So you just pass the data. The mean count. Oh, okay. The mean count is the minimum number of times that a word should be presented in the corpus so that it could be represented in the model. Sometimes you remove words that are just used once because they may be typos or they may be some made up word that nobody uses, right? So you can have a mean count. For example, if in the whole corpus, the word hello is used only once and the mean count is 2, then the model would not find any embedding for the word hello. It would just discard it. So you can have a mean count. It's usually helpful for many rare words and mostly for typos, like typos that only happen once and are not very useful. You have a vector size that can be size of the embedding vector that you want to train. So, I mean, the size, as you said, the size could be less than the vocabulary here. So in one hot, the size of each vector should be the size of the vocabulary because one position is 1 and the rest are 0. But in our new embeddings, the size of vector could be smaller. But of course, the bigger it is, the more information it could have, right? And finally, there's the window. The window is the number of words in the surroundings that the model gets them and predicts the gap in the middle. So here it sees 5 words around the surrounding. I don't know if it's actually 5 words in 2 ways or 5 words in both ways. I don't remember, but I should look at the documentation. But yeah, it's something like that. So yeah, you can go. So the model is trained to predict the gap. So the loss function is the gap, is the word predictor correct or not? So something like this. But in the process, the feed-forward networks that convert the one-hot words to the word that models are used are trained to find good embeddings due to into backpropagation. Oh, you just pick randomly one. I mean, the middle one, for example. You pick the middle one and the model is trained. So yeah, here, what it does with the data is that gets all the data and makes a lot of training points from it. Each training port is 1 sentence, 1 word removed. Yeah. Anything else? Also from people in the Zoom?
Yeah, I have a curiosity. I don't know if it's really important, but you have this window size.
Yeah.
Does that stop at the end of a sentence?
I think so. I mean, yeah, because I think so. So the 2 words, I think there is a specific token, end of sentence or something like this. I think it differs with the implementation. So it's the implementation detail, but if I remember correctly, it was the end of sentence token or something like that. That would just, in the end of sentence, it would just put that token. So it means that the sentence has ended.
So it's a window that could be, that's in the middle of a sentence, but at the very limits, then it's clicked.
Yeah, but I mean that doesn't happen a lot if you have a big document, because, for example, a document that has 100 words, only for the last 2 or 3 this happens, right? And for all of the other words, it's okay.
But sentence boundaries or paragraph boundaries.
Oh, okay, but I mean, I think it doesn't take a paragraph boundary into account. If I remember, I should check, but it just sees also the continuation of the paragraph. So a new line and then the rest of the paragraph. So I don't think it cuts in the end of paragraphs, if I remember correctly. It also depends on the corpus as well. Some corpora usually remove all the new lines and everything. So it's a very long text. Some corpora also do this. It depends on the corpus. Yeah. And by the way, as you said this, the another art is usually having good corpora. So here, yeah, we don't have labeled corpora, but they should be high quality, because if the text is low quality, the model would not learn as a stuff. Imagine you train the text on a chat that we do together. Like, we usually don't follow grammatical rules. We just type something into Telegram or other social networks together in WhatsApp, and we just write sentences without verbs, with typos. This is not a very good training data, but something like Wikipedia, encyclopedias, Stack Overflow, these are good training data. And companies are struggling to find training data. You may have heard lawsuits that OpenAI is facing for finding good training data, like going into disputes with companies. And yeah, so good training data is important. Here, yeah, we don't need to have labels. I mean, for now. So still, ChatGPT is also trained with some in the label that I will get to it in the second part. But yeah, for now, nothing. It's fine. Then you train it. The data, the total example, which is just the length of data, maybe that's even optional, and the number of epochs. So we just trained it, and then you can find the vectors by WV, the property WV of the model will tell you vectors, and there is also a helper function for similarity, which finds the cosine similarity between 2 vectors. So this is the cosine formula between 2 vectors, and we can see, for example, here that similarity between like and love are more than like and parameter. So it means that somehow it has captured the model, even just 50 parts, has captured that like and love are more similar words compared to like and parameter. So yeah, I mean, it's very simple, vector similarity, and I think the whole Copilot can complete the whole thing for you. So it's very simple. Yeah, there is a challenge here. What do you think if I write the vector similarity like and hate? What would it come? Would it be closer to this, closer to this? What value do you guess? Would be the similarity between, for example, like and hate, or love and hate? Well, not that much high, but I think in the cosine it could be negative, right? Yeah. I think cosine could be negative. But okay, what do you think? And like you can all guess. What is the similarity between like and hate or love and hate?
He's trying to be orthogonal when they're not related.
So I mean, yeah, as you can see, like and parameter. Oh,
So then they should.
I mean, yes.
Should be a strong correlation.
You're right, but there is one problem. These models do not know the real meaning of the words. They are just trained with co-occurrences. And do you think such a model can learn that love and hate are antonyms or opposite words?
No, it's
Why? But why? Yes. I mean, the thing that people actually found is that when you train such models, effectively, they imagine a document, a Wikipedia document that talks about a love story, drama story. It usually has both words love and hate in it. So they usually co-occur. And that's the challenge. And you can see if we find this, it's even more than similarity between like and love. So it means that like and hate, at least in this corpus, were more co-occurrent. And this is a big challenge. So sometimes people you may have seen in social media that said LLMs, large language model, ChatGPT doesn't understand doesn't understand antonyms. This is how they are trained. So yeah, it can't find these words are opposites. And that's a big challenge. I mean, there are ways to mitigate this. I'm not saying we are stuck with this, but just wanted to say, yeah, this simple training method does not provide any clue to the model that these are two totally different words. This is just a measure of co-occurrence, words that come with each other. And yeah, like and parameter does not come with each other unless someone talks about their love to deep learning. Maybe just want to read it. I love deep learning. I love training parameters. Yeah, then they co-occur. But like and love come a lot, and like and hate come a lot. Imagine there's a book about a drama story. I'm sure there are a lot of like and a lot of hate maybe on the same page on the book. You may check. I'm sure there are a lot. I mean, I'm sure because the scores are more, so it means that there are a lot. And this is the downside of these models. So we should not rely on these models to find meanings in a sense that we think that these models mean the same thing, but more like these words are in the same domain, are in the same topic, thing like this. So these models mostly find this, not the same meaning of the words. Okay, this is something to find. Maybe, yeah. I'm sure there are some graphical tools maybe in the internet so you can play with this and find this. Maybe like you put two words and then there's a slider how much they are similar or not. But yeah, this is one challenge that we also usually have with chatbots. So previously, before the GPT era, when we wanted to make chatbots, we sometimes use similarity metrics. And when people, for example, ask the chatbot, please don't write that. Please don't do this. When we found the closest question in our database, it was usually the opposite. So please do that. And sometimes we did this and this turned to that. So yeah, this is a challenge that we always need to think about. These models don't learn opposite, don't learn meanings, but mostly learn domains, learn co-occurrences. Okay, what do you think would happen if we train the model for more epochs? Here we trained for 50, and if we train for 300, for example, 6 times more, how do you think the numbers would change? Imagining imagining it doesn't overfit, because imagining it goes better, like the model improves. If the model improves, how do you imagine the numbers to change? Yeah, exactly. So we expect the gap between these two, like this to here, to be more, because the model learns the occurrences more, and this should be further apart from each other. And we can actually see that it is true. So here, from 15 and 0.5, we went to 21 and 0.2. So as we train the model more, the similarity between light and parameter goes down and down because the model learns that there's no similarity between light and parameter, unless we have some tweet about deep learning. And also like and hate also goes up, interestingly. So it's similar to like and love. So more epoch doesn't solve that issue. It doesn't solve that issue, but it's better because the words that are co-current have more larger gap compared to those that don't. So any question? Oh, love and hate. We can. I think we have the results here. So let me just do it. It should, I think, work. Similarity. No. Love and hate. Let's guess. What should it be? I think it should be around this. I'm sorry, around this. I assume, but let's see. A bit less, but yeah, almost around the same. Yeah, this is not too far from, but I guess. So yeah, we can also try other words. What do you want to try? Because if you train this yourself, it will take a long time. So I can just try. What do you think is good to try? I actually tried with my name, but it threw an error because it was not in the vocabulary. So I mean, this is also a challenge. If a word is not in the vocabulary, but ideally, if you train a big model on the whole internet, it would not happen. I don't think GPT has any word that is not in this vocabulary because it's like trained on a lot of data, unless you invent a word yourself, of course.
So you're saying that the similarity rate is from 0 to 1 and 0 to 1.
I mean, I think it should. I should find the how exactly this similarity is implemented. This method. It says cosine similarity, so it should be also negative. Yeah, but in the documentation it doesn't say. So I mean, these are vectors, right? I don't know how this method compares the similarity. If this is a cosine similarity, I think it can also be negative. Yeah, but yeah, I have to find words that do that. So yeah, but these are vectors, so you can even print the vector yourself and do like vector anything you want to them. That's it. Okay, I think that's enough, right? We can go back. Let me stop this. This thing is very bad. Let me hide it. Hide floating missing controls. Let's go for BART. So now we know how to form the inputs. What the hell are they doing? Now we know how to form the inputs to the models, right? Previously, the models that had limited label data had also limited semantic information of the words and the similarities and their meanings and the equivalent vectors. But now we have models that work with embeddings, mappings that are trained on a vast corpus. But they still work with limited label data. So now the model that we have, imagine the classification model, we have 5,000 examples classifying between happy and sad. Yeah, the word equivalents are a lot. Like, the word mapping is very good. So we have a very great mapping from each word to the vector, imagining we have a very great mapping. And we just now use those mappings, train a model to get them and predict happy or sad. So this is the model that we have now, right? This is what we have achieved. But still, those 5,000 sentences may seem low. They are not usually still enough for model to capture a lot of things. And we can also see this in traditional NLP approaches. Even with the best LSTM approaches, we sometimes had, on some data sets, we had very low accuracies. You can see in the paper, or I think I have some stats, but in difficult data sets, we didn't have very good accuracies. So we still have the amount to improve. The next step is that why not also train the model itself or somehow use the vast amount also for the model, not only for embeddings, but also for the model. So we had those 5,000 sentences. There are not a lot, but we had a very big amount of data that we used for finding embeddings. Okay, perfect. But after that, we are just now using the 5,000 sentences, which are not a lot. And we can't also label all the text in the internet because it needs a lot of human effort and we need to pay a lot, so we can't. Can we find some way to also use those big amount of data also to help our models? Anyone has any suggestion from what you learned in the Vision Week? What's an idea that you can do? Sorry. Okay, and we can just go. It's I think you have been transfer learning, right? Or no? You're not in the Vision Week? Okay, I'll just cover it in more details in that case. No worries. So the idea is transfer learning. What is that? In transfer learning, we have two phases of training our models. Instead of just training, we have a pre-train and a fine-tune phase. So previously, okay, imagine we have the embeddings for now. Forget about embeddings. We have very good embeddings, like they're perfect. Then until now, we had the data set 5,000 sentences, happy or sad, and we trained the model. But instead, here we want to do something else. We want to first pre-train the model on the big corpus, somehow, I will say how, on the very big corpus that we had. Then we fine-tune it on the small data set that we have. We usually call this a kind of transfer learning because you're transferring from one domain to another. So here, we still use the big data set, the whole Wikipedia or anything like that, in our pre-training phase. But then we fine-tune the model as a second step on the smaller data that we have, so that the final model finally knows to classify between happy and sad. How does that happen? Because that may seem a bit weird. Like, how do you pre-train on a lot of data that has no labels, and like it's a bit weird. We will go over it, and we will cover actually two architectures that do this, BERT and GPT. We'll cover them today. Both they do this approach, pre-training and fine-tune, and we will cover both of them and their specific architecture today. And that's basically the main thing that you need to know from NLP these days. Like, this is the hot topic now. So people do pre-training plus fine-tune. I think actually there is also a specific session on fine-tuning techniques later this week, I think, in the syllabus. So that would be specific to fine-tuning and like finding data sets, introducing a library called Hugging Face for helping with this. I will not go over those details, but okay, we'll cover the main architecture here. So a model, imagine a transformer model or any model. Usually we can split it into a body and a head. Body is the main weight of the model, and head can be just the top part or the top layers or a number of layers on the top that are task specific. This is the general idea behind transfer learning. So we can split our model into a bigger body that is constant between tasks and the head that is task specific. And then we pre-train the whole model, including the body and head, but we fine-tune the head. We can also not to do this split and fine-tune on the whole thing, but that's also another thing. So, but this is one idea, that we split our models into a body and head. It's like this. Imagine this is a model A. This is the traditional approach. I think I'm far from the laptop, so maybe just stay here. This is the traditional approach on the left. We had a model A and model B. Each one had a certain data set on their own, for example, the 5,000 text, and provided some predictions, right? This is the normal supervised learning that we had until now. Two models, two different data sets, and end. But imagine we split the model into a head and a body. We train it on the first blue one. Imagine the data set from blue one is a very big data set, like the whole Wikipedia. We train a very good model, but it does not have any ability for our task, for classifying between happy and sad. But the body, the weights in body are very good weights. I don't know how to say it, but the weights are useful. We can see how. And then we use the same body, we discard the head, but use the same body and move it into another model, put a head of our own, and then we do another training, which we call fine-tuning on the right in our smaller data set. So we don't touch the body, but we touch the head. And then we have our new model. That ideally, this the model on the right should work better than the model on the left, because the model on the left only uses our 5,000, but the model on the right not only uses our label data set, but also a lot of good quality text on the internet, for example, Wikipedia. So that's free. I will go over it, but yeah. So the procedure again is to train the model on a vast amount of data. Then for each specific task that we have, we train the head on that task. Even if you do this, a very good point is that you can for example spend a million francs or something like this, train a very good model on the whole Wikipedia or something as big as that. Then for each task that you want to do in the NLP, just replace the head and just do a fine tune. And then you have a very good model on that task without the need to train from scratch. So this is the idea of transfer learning. And you can think, okay, why don't people do this? They create a model and then share it with everyone. The answer is that they do this. So we have some platforms such as Hugging Face that you will see later this week in detail. It's called Hugging Face. This is a model that people share models. So you create a model, you share it, and people can download, replace the head, and fine tune it themselves. It's something like GitHub, but for trained models. So yeah. What's the idea behind this? During training, the weights of the body learn usually broad features of the source domain, not specific features. It can't classify between sad and happy, but it learns the language. It learns sentences. I mean, nobody knows exactly what they learn because they're usually black box, but they somehow learn. It's like a kid that is learning with a lot of things. Imagine you want to train a kid, like you have a kid, and you want to train them to be a successful person in life. You don't just when they're just born, you don't start with telling them, uh, okay, this is a good, this is bad, or thing like this. It observes your actions, right? It observes your actions over time and somehow learns some basic stuff from it, and then you can fine tune your kid with specific instructions. This behavior is good in public. This behavior is bad. This is somehow similar to how these models are trained. So first, they are trained on just a lot of unlabeled data that we'll see how, specifically how it's implemented. They they train on a lot of unlabeled data, and then the model is strong enough so that with a simple replace of head and a simple instruction similar to a kid, it can be very useful for task specific things, such as classifying emotions or between happy and sad or things like that. It allows much less training data on our side to be effective. I mean, here I'm talking about label training data. The internet training data should be a lot, but our training data could be less. For example, maybe with 1,000 sentences, we can have equivalent accuracy of 5,000 sentences on a more traditional model, for example. Interestingly, people later found that it also learns good embeddings in the process, this process as well. So we can just use here also to train the embeddings in this model, because it's the same thing, right? Embeddings are also trained on a big corpus. So we can also have the embeddings here. So instead of a head and body, we have embeddings body and head. We can have it like that as well. So we train embeddings also in the same place, and that's how now models are trained. Actually, OpenAI, when it was founded, it was a pioneer of this stuff well before the ChatGPT era. It was 2018. They were publishing papers about this, and nobody could have guessed what they're doing. But yeah, now we guess why. So this is the whole idea of transfer learning. Any questions? Yeah.
What's the feedback here? So how do you train the body?
Oh, I'll talk about this. I'll talk about this. Yeah. So because you don't have labels, it's not a simple loss. I'll talk about it how it's trained. Yeah. The head is simple, right? The head is the exact task that you have. So it's the same backprop as we know. But just consider that in the last part, you sometimes freeze the body. You can do this in PyTorch, it's easy. You just freeze those layers so that they are not updated in backpropagation. You can also let them update. Also, sometimes people do this. They don't freeze, but because fine-tuning are on small sentences, they don't change the body a lot. And that's also sometimes helpful. So you may choose to freeze them or not. This is your choice. But you don't start from random body. Yeah.
So also then what's the class? Is it in the blue?
Yeah, I'll talk about it. We usually use math language modeling or some other tasks, but we'll talk about two tasks that people use for blue. Yeah, the main topic of the rest of the lecture, actually. Yeah. So yeah, we'll cover it. For blue, we'll cover which task. For red is obvious because you already know our task. But for blue, we need to find some task because there's unlabeled data and people have done two main things that I will cover today. All right. So yeah, this is the question that I actually want to cover. How we want to initially train the model. What's the objective? As you remember, in CBOW, it was predicting a gap word. And here is also something similar. One of the approaches that we do is also somewhat similar to predicting gap word, but with some modification that we'll go over it now. So before getting to that, we want to see how transfer learning using transformers. But okay, the words are similar, transfer learning, transformer, but they're two different things, right? They have nothing in common, but we can use them together. So we can use transfer learning with transformers. So we can have the same head and body architecture in transformers. And that's the backbone of today's NLP systems. They use transfer learning for its benefits and also use transformers because they are powerful models. So they use both. These are two ideas beyond a simple sequence to sequence that works with an RNA. So we had this transformer, right? We had encoder and the decoder. This is the idea of BERT. Maybe let's cover here. So we have an encoder and a decoder, right? One idea that people had is to ignore the decoder altogether, discard it, only have the encoder. And that's how BERT was born. So BERT is a model called bidirectional encoder representation from transformers. BERT, I think they just used BERT to find the similarity between to the cartoon character because they use the same logo, I think, in their paper. So yeah. Anyways, so this BERT model. What's BERT? BERT is just the encoder part of the transformer. So you can see here, right? I just cut actually the picture. So it's like you just cut this part. You ignore the decoder. And then the model that is here is called BERT. I mean, yeah, this is not only BERT because you need to also do some modification, but the architecture of BERT, which is the model that we are covering today, is the encoder part of the transformer. So for now, ignore the decoder part. Imagine we only have the encoder part, and we're going to cover one model called BERT that works with the idea of transfer learning. And now is commonly used for text classification and a lot of tasks. It's used a lot of papers, and there have been multiple variations of it. So we want to cover this today. I think this hour we will cover the architecture of BERT. The next session would be seeing a code of BERT and then going to GPT. I think this is the plan of today, roughly. So what is BERT? You can see again the architecture there. So this was invented by Google AI team in 2018. There are two variations of BERT. One is called BERT base and one is BERT large. The only difference are I think the number of units of the encoder used and also the number of multi-headed attention, because you remember attention was multi-headed and you can have different heads, the number of heads are different. So there are the two differences between these two models, BERT base and BERT large. And they have a lot of parameters, like 110 million parameters for BERT base and around 300 for BERT large. So what they do here? We have the embeddings. We also have the position embeddings. It's obvious, right? We don't just put the input in a certain way. We put the input in a certain way. With each input first comes with a CLS token. This is a specific token that is before each sentence. CLS, I think, is a stand for classified, but I don't know. So it's a certain token, like a certain token that they define, CLS. Then one sentence. Then a SEP token, and then another sentence, and then another SEP token, and so on. This is how text are input to the BERT model. So they get all the text from the Wikipedia or like the sources that they use. They put it in this format to the model. So they have two sentences at a time, separated by the SEP token and also the CLS token in the beginning. I will talk about the role of these tokens later, but yeah. And also we have a segment embedding that's a certain value to show which word belongs to the first sentence and which word belongs to the second sentence. Here, E of A is a certain value for the first sentence, added to all words here. My dog is cute. But he likes playing with the second sentence, so E of B is another value that is added. It's something like the positional embedding, but not only for the order of words within a sentence, but to say which word belongs to which sentence, right? So these are the things that they add to the model. The idea is that the model learns where a sentence finishes and another starts. We'll talk about it. But any question until what they add and how they form the input of the model? So we have not talked about training now, right? It's just the input of the model. So the input of the model like this. Any questions? Yeah. Two specific values. I think they can be trained using backprop. They can be found. But there are two specific embeddings. So positional embeddings was one value per word. This is one value per sentence in the data. Yeah. The same thing, but one value per sentence. So it's kind of it signifies the order of sentences in a document. You can see like these are the things that people had to come up with to differentiate NLP from simple time series, because okay, we don't have the idea of sentences in a simple time series, but we have them in text. So they did this. All right. I think we can go forward. So what happened? I think it's okay. Okay. So what's how do they pre-train BERT? Okay, if you remember, we had the pre-train and a fine-tune, right? Fine-tune, as I said, is simple, but what pre-training we need to see the blue part. How do they train us? They do two things to train a BERT. First, it's called masked language modeling. It's around the same thing as filling the gap. So they pick one word in the sentence, they replace it with a certain token called mask. So here, for example, I'm attending a summer bootcamp. It's one of our training data. They replace randomly the word attending with a mask. And then the model should predict that word. So it's very similar to what we saw, right? The only difference is that the continuous backup word was a simple neural network, but here it's a transformer-based model, right? So with the input that we saw. So yeah, we just predict, and the loss function is just like the criteria to see if it works well or not. Is that attending should be the same as the word that was originally instead of the mask. The aim here is to help the model learn word level information, of course, right? So this is not too new for you. One specific thing, the input of the BERT model at each time is, I think, 512 tokens. But most sentences are less than that. So you usually add some padding tokens. Paddings are certain tokens that you add them to fill the gap of 512 words. Because, sorry, 512 tokens. Tokens are not words because ing like is another token. Here I've mixed them, but actually attend and ing are two separate tokens. So I mean, it's an example, but in real world, the tokenization is a bit different as we saw. But yeah, so we add padding to fill all the 512 tokens at a step. What's the downside of this? Is that the model cannot, if, for example, we use this model for predicting sad or happy sentences, it can't work with sentences that have more than 512 tokens, right? So this is the downside. What should we do? We should maybe summarize the sentence, crop the sentence, or just throw an error. We can't input sentences more than 512 tokens to the model. So there is a certain, we usually call it context size in transformers. We usually call it context size. You may have here in the news, OpenAI announced that the context size of the model has increased from this to that. That means this. I think GPT currently has a context size of 128,000 or something like that. And I think Google's new model is like 1 million context size. So BERT was in 2018, 512 was a lot then, but now it's nothing. But the architecture is the same, right? So we add paddings until the sentence gets into the context size, and then we predict the mask. So that's it. Perfect. So this is one thing that they pre-trained BERT with. And the other test that they also optimize for is predicting text continuation. What does it mean? Imagine here, I am, okay, there's a mask still. I am attending the summer bootcamp. Then the next sentence in that document that I wrote is that I learned a lot. These two sentences come after each other, right? So it should predict a yes token. I mean, yes could be a 1 or 0, a certain token, saying that these two sentences come after each other. However, in the training, they sometimes replace the sentences with random sentences from the documents. For example, I'm attending summer bootcamp, Steve Jobs was the CEO of Apple. Okay, these are certainly not coming after each other. So here the model should find this and predict no. This is another thing that they do. So they get a very big corpus, they replace some words with mask, and they also replace the order of sentences sometimes so that the sentences are not following each other. They are from another document, like another Wikipedia document. And then the model should find if the sentences are related or not, are coming after each other or not. These are the two tasks that the model trained. And they found that when they do these two pre-training tasks, the weights are very strong. And if they just do the fine-tuning, it works very well on a lot of tasks. And actually, there are a lot of like a lot of tools that we use maybe every day that work with BERT for its family. So it's a very it has been shown to be a successful task. Later work showed that the masking part is more important than this part. Later work showed that if we remove this part, the performance hit is not a lot. But if we remove the masking part, the model does not learn anything. So the more important part is masking, but the authors of BERT did both. So, I mean, they also did some minor other things. Sometimes instead of masking, they replace some random word from another document. So, but I think with a very small probability to avoid overfitting and these kind of things. I didn't include them because there are some implementation details, but the main two things are the masked language modeling and also the finding sentence continuation. These are the two main new things that BERT did. Any questions? All right. Yeah. So yeah, sentence as you remember, the sentences are separated with the word sep, certain token. So each time the model sees two sentences at the time, and sometimes they are after each other, and sometimes they're not, and the model should predict that. So the model actually this is a model that each of them have an output, right? Each cell has an output, and both of them are in the one step. So the model should both identify the word of the mask and put a yes or no here at the same time. Yeah, exactly. I mean, there are a lot of sentences in the document, right? There are a lot of pairs that it says. It's not specifically one sentence and two sentences. It can be like maybe I am at an example bootcamp comes with 10 sentences in the document, and like 6 of them are after each other, 4 of them are not. And the model should learn this. It's also random, like there is a random thing in the process. So they put randomly, they put something from another document. Yeah. So this is the thing that they do. Oh, what happened? Sorry. Okay. All right. Perfect. So we have the BERT model again. Always you should also remember the padding. So in the code also it asks you for what padding, what kind of padding to insert, how you should insert it. But yeah, always we have a padding that fills the rest of 512 tokens. Then the model, first of all, predicts the word instead of mask, the correct word that should come here. This is one task. And the other task is that it also predicts if the two sentences come after each other or not. Ideally, by training the model with these two criteria to find the gap words and to find if the two sentences come after each other or not, the weights of the body are trained in a way that understands the language, understands how the BERT understands how language works. It can understand a lot of things from the text. I mean, we don't know exactly how because it may seem a bit counterintuitive. Why finding the gap words helps us better in some other irrelevant task? We don't exactly know why, I think, but that's one of the miracles of deep learning, but because everything is a black box. But the weights are trained in a way that predict words that are actually useful for that the weights are actually useful for us. And we can use the same weights in a body, just maybe replace the head or do a simple fine-tuning and use it for a lot of different tasks. Also, the BERT model in the specific trained way, you can easily download it. So if you go to Hugging Face, I mean, you will also see a specific fine-tuning lecture about this later in the week, I think. But yeah, so you can just open huggingface.co, I think, huggingface.com, go, something like that. Then you search for BERT base or BERT large, and you can just download the model. So I think the BERT is around 490 megabytes or something. It's not a very big model compared to today's standards, but it's almost half a gigabyte. It's just actually all the weights and biases of the all matrices here. So they have trained the model with a big corpus and have made it available to you. So you can just download it, replace the head or fine tune or do things like this and make it your own model. Also, people have been done more things with it as well. For example, we have BERT for certain languages. For example, we have BERT German. That is the same model, but trained on a big German corpus. And it works better in German data if you fine tune, because you can also fine tune the English model on a German data. And actually, I tried it in previous, and it also works to an extent, but because at the end, it's a kind of training, right? You are still training something on your data, so it learns something. But it's a waste of resources because you are wasting all the body weights that were specific to English words. So it's better if you are, for example, making a model for a system to be used in a German environment, in a German language environment. You can just pick BERT-based German as an example. There are also for other languages, BERT-based German, and then fine-tune that model to your specific data. Also, there are multilingual BERT models. So BERT is a family. We have also Roberta, Diberta. These are all families of the BERT model that each have differences. And some of them are also multilingual. I think one is called XLM, something like that. That was developed by Facebook. Meta, currently Meta, which is the multilingual model based on the BERT architecture. So they put not only corpora from English, but from a lot of languages. This is good for tasks that you want to fine tune, that your data is from multiple languages. And you want a single model to work for all of them. In that case, you can fine tune a multilingual BERT model. So we have a ton of models that you can use for different occasions that are very useful. So how do we do fine tuning? So until now, we have the actually trained, we have the pre-trained model, the body that has a lot of weight and everything. Now we want to fine tune the model. Imagine we want to fine tune for fine tuning for filling missing words. It's easy. You just use the same thing, right? Even the BERT base can fill missing words because it has been trained to do that, right? Even without fine tuning, if you just download BERT base, you can use it for filling the missing words in a document. It can be useful, for example, for a writing assistant, or you are developing a tool to like write people to write something, and you can find missing words and add them. You can just use the simple BERT base for that. So yeah, you don't even need to find unit sometimes if you're just using it for the simpler architecture. And I think we can even show, yeah. So here this is a Hugging Face website. This is something like GitHub but for trained models and datasets. So yeah. So here I just searched BERT. BERT case means it's also has the case of words like capital case and small case. There's also uncased version, which is trained with everything compared to everything converted to lowercase. It depends on your task. So there's like you can download files here. You can even say use this model. It gives you some quick code that you can use the model. It's very useful. Like this is a very good website. What I want to show you here, actually, there have been 5 million downloads on only last month, so it's still trending. Yeah. Also, the size of the model you can see here, like there are a lot of stuff. And this is a place that you can try the model online, which is very cool. Here you can see there's an example that they just did. The goal of life is mask. So the goal of life is survival, love, happiness. These are the probability returned by the model. So in the same model, there's the softmax on top of it. There's just a softmax on top of it, on top of the scores that converts the probabilities for us. And then it returns the words. Any sentence you want to try, anyone? Maybe just sentence that we just said. I am attending the summer bootcamp. I want to see what it would say. The first time you should load on their servers, and after that, I think it's pretty simple. I'm at the summer bootcamp. Yeah, yeah. I'm in. I'm on. On is not very good. On the summer bootcamp, I'm attending. I'm having. I expected enjoying as well, but yeah. Okay, you can see, right? So this model is actually just this is a very base BERT model, no fine tuning at all. It's good for filling mask.
If we change the points on periods to exclamation mark, it change the context.
Like this? Yeah, maybe it will change. Good idea. Enjoying came here, but didn't change a lot. Just I think it's not so very important. Like they're close. It didn't change a lot, but yeah. One trick of this is that it's not good for completing text. So because it's trained to find a gap in the middle of a text, so it's not good for completing. It can be used, even the initial one is kind of completing. But here, imagine, okay, we have the goal of life is love, and then we want to complete this with another sentence. Let's see how it works. You see, it's not very useful. I wanted it to provide the next word for me, but it didn't work. So it's not good for text generation or text completion. For that, we need another model, which you can guess is GPT, that we will cover it. But yeah, for BERT, BERT is usually, okay, the base model works for filling the mask, which is very good. Another thing that the model is good is another task that is trained on. What's that? Two sentences are similar to each other or not. No, sentence BERT should be something like here. Maybe this. Oh, it's not a trying thing here. I wanted to have it, but there is a code actually here. You can see. So these are two sentences that they can find the encodings and like compare them. But yeah, okay, we don't have the trying thing here, but you can. What you can do is to also do the task of if the two sentences come after each other or not, because the model is trained to do that. You can also do that task without fine tuning. So the very base BERT model works on those two. But what if you want to fine tune? The main task that people would fine tune BERT for, one of the main tasks is to, there are some main tasks. Some of them, one task that previously was very common was to find parts of sentences. What do I mean? For example, you have a sentence, you want to say, okay, this is a verb, this is a noun, and things like this. You can fine tune a model to output the meaning of each word, or I mean the role of each word in a sentence. You can fine tune a BERT for that. But one other task that is super used and like is very common that I will show in the slides now is here is classification. For classification, it's like classifying a sentence is happy or sad, or classifying is, well, this thing is irritating. Every time I should hide it. Classifying is something is happy or sad, or classifying is an email is a spam or not, or multi-sentence classification, or things like that, multi-class. So for tasks other than filling missing words, and also sentence, if two sentences come after each other, you need to fine tune. What people usually do is to use the output of this token. There's a CLS token, and use the output of this word in our fine tuning criteria. So we fine tune the model to, for example, imagine it's about happy or sad. Happy is 1, sad is 0. I enjoyed attending the summer boot camp. This should be 1. I hated following the summer boot camp. This should be 0. We fine tune the model to output 1 for this sentence and 0 for this sentence. We usually fine tune on the output of the CLS token. This is usually how it's done in practice. So here we fine tune the model when we see this sentence in this neuron, in this unit, output 1. And when we see this sentence in this output is output 0. And then we fine tune this model with this approach on, for example, our 5,000 data. Something like that. And actually, it works very well. So yeah, I think we can see even benchmarks of emotion. For emotion data, let's see. It's a data set for emotion recognition, as I just said. There are, I think, 6 emotions here. Yeah, you can see, like, this is, for example, I'm feeling quite sad, which is label of 0. There are 6 emotions, I think, sad, happiness, anger, and these kind of things. And I want to see if there's a leaderboard. It's not here. Leaderboard. I want to show you how much people have found accuracy in this data set. I don't know if there is anything here. Oh. Give me a second. Maybe here. So this is the data set, by the way. For example, here I didn't feel something, sadness. I'm feeling Gucci's anger and like this kind of thing, right? So each sentence, these are small sentences with labels. It's a very good toy data set for NLP task. It's not very big. I think the whole data set is 16 megabytes, so you can easily do it on your computer, and it's very good. And also a lot of sentences, so it's like multiple thousand sentences here. So yeah, I want to see if there's any leaderboard. Oh yeah, no, it's not here. Emotion. Maybe this one. I don't know if it's the same data set, but yeah. Anyways, I can't find it, but I will. I will later take a look into that. So yeah, there are some leaderboards on the internet that you can like submit your model with that data set, and then everyone says, "Wow, yeah, I beat the state of the art." And actually, for emotion, with a simple BERT model, I think I was able to find an accuracy once of 90 and something, which is very high. Like accuracy of many deep learning models usually I stay at maximum 70, 80%. But for emotion, you can easily have an accuracy of 90 and so, close to 100% accuracy with a simple BERT model. So this model works very well, but still, it's not. I mean, BERT is not the state of the art at all. Like nowadays, I think no one uses BERT because it's super old. You may consider how 2018 is super old, but it is. So yeah, 2018 is now considered very old, and now there are way better models, but a lot of them still are on the same architecture of as we just saw of the encoder. Question. One question here. Why do we output the prediction at the start from the CLS? Why not at the end? because maybe you can say, okay, at the end, all sentences have been seen. So why do we use the output of this unit and not put it in the end of the sentence? Anyone has any clue? Why does it work? For classification, I mean.
To just pragmatic, you don't know if they're ragged right. You don't know how long they're going to be, so you have an easy way to access it.
Yeah, exactly. That's something. And also, it's not important because it's attention, right? It's not an RNN. So in the end, all models that can attend to each other, and even if we put it on that side, it would work the same. But we usually put it here so that we can fill the rest with the text that we want. So it's just something that was decided. It's not different if we put the CLS in the end or in the beginning in practice, because the model can attend to each token and it doesn't have any kind of recurrence. If it was an RNN, it would matter, right? If it was an RNN, it would matter, but here it's just the positional encoding that's different. And we can just put the CLS because it can see all the sentence. If it was an RNN, it would be nonsense because it hasn't seen any of the words until now. But because it's an attention-based model, it's a transformer, it can attend to any of the words in the whole sentence. I enjoy attending and can use them. And actually, people have, after fine-tuning, you can do visualizations to see which words do they attend most to and things like that. And actually, you can see.
Parsa.
Yeah.
You forgot to change the screen on Zoom.
Oh, yeah. I mean, it's still the same slide, but yeah. Thank you. Okay. So I hope you see it now. So yeah, for people who are on Zoom, I was saying that the CLS token can be also in the end or anywhere else. It doesn't matter because it's the attention model and attends to every token in the sequence. What I was saying is that also people have found by visualizing the attention weights, which tokens usually the model pays more attention to. For example, in the emotion classification, we assume that words such as enjoyed and hated have a more direct effects and maybe more attention weights compared to bootcamp. Because I mean bootcamp is a word that describes the context, but for emotion classification is not very important. But enjoyed and hated are important. But for example, if we have a model that classifies the location of something happened, for example, if it's an educational thing or an entertainment, then bootcamp is important because bootcamp is not entertainment, it's educational. So oh, you can visualize the weights. Yeah. Yeah, exactly. I think we can even see it. I mean, okay, so there's something. I mean, we should run it on our model, but here you can see something. Like which words attend to which words. This kind of thing. This is something that we have at least. I don't know if we have also something like which words are more important to the classification. I think there should be some word. Maybe you can configure this visualization tool. There's not an online tool, seemingly. You should download it and use it with your own code on model, but yeah. So these are some stuff that you can do here. Oh, they're cool visualizations. What can we see? Oh, okay. You can see the CLS like connects to which words. Here is go to CLS. It's maybe I don't know. It goes too fast. I can't even see. But yeah, I mean, ideally we should see here. When we use the model and fine tune it, ideally the CLS token should maybe attend to words that are more relevant in classification. I hope. So yeah, I don't know if you can pause this. I don't think so. Try out the normal interactive collaborator. All visualization preloaded. Let's try this. Scroll down for preloaded visualizations. Okay. Oh, this is it? Okay. So what can we see here? So this is just a simple BERT, not fine-tuned, right? Yeah. This is just from pre-trained, as you can see, and there's not fine-tuned thing. But we can see which, but it's not very relevant, right? Because I want a fine-tuned version. Don't we have any fine-tuned version? No. It's sad. No, we don't have any fine-tuned version, but if I will, I'll show you. So yeah, but I think if we fine-tune, we can find some visualization here, and I think I've seen people have done that. Find visualization to see which words are attended more, and actually this is the way also to debug large language models. I think also OpenAI has just recently released something that you can visualize some visualize some links between different tokens and these kind of things in GPT to find bugs in the model and like why a model behaves a certain behavior. But I'll take a look. Maybe I can find something. Yeah. 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 Here we have also there we had a last function, but we invented it ourselves. So the function that we had was actually finding the master word and finding the correct label between yes and no for the two sentences. But we invented it ourselves from the data that we had. But here we have the labels from humans. So here we are not inventing anything. The 1 and 0s are a corpus that are labeled by a human, by a researcher or anything like that. And then we are using that. So yeah, as the time is also up, the beginning of the next session, we will first see a code together about fine tuning. We won't go into details because you have a fine tuning session. And then we go into two downsides of BERT. One downside we will just cover quickly, and the other would introduce us GPT. And I think that would be the afternoon session. Any questions? I think we ended up actually very good on time. So yeah. Perfect. So I'll see you in 1, I think. Is 1, right? Perfect. Let's have a lunch and then come.